Welcome back everyone, Houston Math Prep here with our video on left-hand and right-hand Riemann sums. If we use rectangles, we're actually able to approximate the definite integral of a function from a to b. Remember, this represents the area under the function, the exact area, on this interval a to b. So I have some curve, and this definite integral represents the amount of space, the amount of area we have between x equals a and x equals b, between the function and the axis there. The way we'll start to build rectangles, we'll split the interval into some number, we'll call it n, of equal subintervals. So I have my interval from a to b, and here I've split it into, you can see, 4 equal pieces, each having the same width. You can see here that each subinterval is going to be the width of the rectangle that I'm building. You can find the width of each rectangle if you just simply take b minus a, that's the entire distance from a to b, and then break it up into n pieces, however many rectangles you're using. That will give you the width of each rectangle. We're going to call that delta x. So each of our rectangles based on the width of each subinterval, we're going to call these delta x. For a right-hand sum, we build our rectangles so that the top of each rectangle is the same height as the function on its right-hand side. So you can see for each of our rectangles, the top right corner of each rectangle touches the function, and that's how you can tell that we've used the right-hand side to construct the height of each rectangle. If we want to get the exact height for each of our rectangles, then we could plug in the x value on the right-hand side of each rectangle into our function, into our f of x, and get the height. Just a notation thing, we'll call the height of our first rectangle f of x1, the height of our second rectangle f of x2, so the height of our third rectangle here is f of x3, and our last one we'll call it f of x4 since I have 4 rectangles. The area of each rectangle, of course, is going to be the base times the height. We know that the base, the width of each, is going to be delta x, we said. And the height of each is going to be based on the y value we got when we plugged in these right-hand x values into our function. So we take a formula of width times height, and we take the sum of however many rectangles we found. That's going to give us our approximation for the area. This expression here that represents summing up a certain number of areas of rectangles, we call this a Riemann sum. If we wanted to switch from a right-hand sum to a left-hand sum, then we'll build our rectangles so that the top of each is the same height as the function on its left-hand side. So here you'll notice for a left-hand sum, the top left corner of each rectangle is touching the function, and so the height of each rectangle is based on the function height on its left-hand side. So in this case, if we want to get the height of each, we'll simply plug in the x value on the left side of each subinterval there. Let's go ahead and work an example. We're going to use a right-hand sum to approximate the area under the function 1 over x on the interval x equals 1 to x equals 5 using 4 rectangles, and I've got my picture already drawn here. So if we are using an interval from 1 to 5, so think about on the number line here, right, we are going from x equals 1, so this is our a here, to x equals 5, this is our b. And if I'm using 4 rectangles, you can tell from our picture here, I think, how wide each rectangle is. But let's say we didn't have this picture, and we want to figure out what is the width of each rectangle. So the first thing we'll figure out is delta x. We're going to need our width first to be able to do this approximation. So remember, our width of each rectangle is going to be the total width of the entire interval divided by the number of rectangles we're using. So in this case, I've made it work out nice and easy. We've got 5 minus 1, b minus a, over the number of rectangles we're using is 4. So we get 4 over 4, which is 1. So from here, even if we didn't have this picture, we would be able to tell that the width of each rectangle is 1. So how you figure out the boundary value for each rectangle, we simply start at the left side of our interval, we count by whatever delta x is until we get to the right side. So I'm going to start at 1, I start at my a here, and I'm going to count by 1s what I got for delta x. So 1, if I count another 1, that's going to be 2, if I count by 1, that's going to be 3, and then if I count by 1, that's going to be 4. Okay, so we've got our boundary values for all of the rectangles you can see. Now if we're using a right-hand sum, then we want to go to each subinterval and we want to figure out which number is on the right-hand side. So if I look at the interval 1 to 2, 2 is on the right-hand side. If I look at the interval 2 to 3, 3 is on the right-hand side. If I look at the interval 3 to 4, 4 is on the right-hand side. If I look at 4 to 5, 5 is on the right-hand side. So these are the numbers that we will plug in to our function to get the heights of each rectangle. Now notice 1 is not on the right side of any rectangle. It's only on the left side of this rectangle here. So we won't actually be plugging in 1 when we're doing a right-hand sum. So to get the height for each rectangle, we'll just plug in these values into our function formula. So my first x value is 2, so we'll plug in f of 2. That's going to give us the height of the first rectangle. If we plug it into our function, we'll get 1 over 2, that's a half. Our next x value is 3, so f of 3 will give us the height of the second rectangle. If we plug 3 into our formula here, that gives us 1/3. You can probably see a pattern coming, right? The next x value is 4, so plugging in 4 would give us 1/4. And the height of the last rectangle would be plugging in 5. And so we'll get 1 over 5. Okay, so I took my x values that were my right-hand x values for each rectangle. I plugged them into my formula, and that gave me the height for each rectangle. So now our area approximation, so we'll go ahead and say area, and we'll put a little curly equal sign here to show that we're approximating, is just going to be our width times our height for each. Now our width for each is 1, right? So we'll have 1 times 1/2. That will be the area of my first rectangle. My second rectangle will be 1, that's the width, times the height, which is 1/3, plus the third rectangle, which will be 1 times 1/4, that's the width times the height, based on f of 4, right? And our last rectangle will be 1 times 1/5. And if we get a common denominator for that, then we'll get 77 over 60, and that is about 1.28, and we have 3 repeating there. Now you'll notice because our function is a decreasing function, all of our rectangles actually leave some space that they're not calculating that they should be calculating if they were super accurate at doing this. So we're getting less area than we should be using a right-hand sum. So we'll just make a note looking at the picture here of this function and telling that we're short a little from each rectangle. We know that this 77 over 60 is actually going to underestimate the area that we're trying to approximate here. Let's go ahead and do a similar thing with the left-hand sum. We're going to approximate the area under the same function, the same interval, the same number of rectangles. So if I didn't have this picture here, I would just draw a number line on my paper maybe and not actually on the graph. But I know I'm going between 1 and 5 again, right? Now, I know that my delta x is going to be the same here because we just did this, but remember it would always be b minus a divided by the number of rectangles. So again, this is going to be 5 minus 1 divided by 4, which is again 1, right? And the way we get all our border values between rectangles, we just simply start at A, we start on the left side, and count by whatever delta x is. So if I count by 1s, the next one is 2, and the next one is 3, and the next one is 4. Now because this is a left-hand sum we're doing, then we're going to look at each subinterval and use the x value on the left of each rectangle, right? So this interval from 1 to 2, 1 is on the left side. From 2 to 3, 2 is on the left side. From 3 to 4, 3 is on the left side. And from 4 to 5, 4 is on the left side. So you can see here we won't be using 5 to plug into our function because 5 is not actually the left side of any rectangle and we're doing a left-hand sum. So we'll just be plugging in 1, 2, 3, and 4 this time. So if I plug in my x value to the function, that will give me the height for each rectangle. So my first x value is 1. Plugging in 1, we would get 1 over 1, also known as 1. And we're going to get the same thing we got before, right? If we plug in 2, then we'll get 1/2. If we plug in 3, we'll get 1/3. And if we plug in 4 for the height of our last rectangle, then we get 1/4, right? So these are the heights of our rectangle. Now, our area approximation for this is going to be delta x times the height for each. So our delta x is 1 for each. So for the first one, we'll have 1 times a height of 1, that's width times height, plus 1 times a height of 1/2 for the second rectangle, plus 1 times a height of 1/3 for the third rectangle, plus a width of 1 times the height of 1/4 for our fourth rectangle. If we get a common denominator and add all those up, we'll get 25 over 12, which is about the decimal 2.083 repeating. If you'll notice here, we have this decreasing function, and think about a left-hand sum. For this picture here, I'm getting actually area that I don't want, so I'm actually overestimating with every rectangle. So we also know that this 2.083 about is actually more than the actual area underneath the function between x equals 1 and x equals 5. We'll also point out that using more rectangles, increasing your number for n, will actually give you a better approximation of the area under the curve. You can see the picture of n equals 4 and how much space we're leaving out underneath the function here. If we increase the number of rectangles to 8, then you can see we're leaving out much less space, right? So from n equals 4 to n equals 8, you can see that we're shorting the area by a smaller amount now. We can see a similar thing with a left-hand sum, so we're overestimating by quite a bit with these first couple, and then we overestimate by less, it looks like, as we go on. But if we increase our number of rectangles to 8, then you can actually see that we are overestimating by less. We have less extra stuff above the function than we do with n equals 4. One other way to maybe get a better approximation in this case would be to use a picture like this that is not a left-hand sum or a right-hand sum. You'll notice that the height of each rectangle is actually based on these points here that I've labeled, and these points are actually in the middle of each of my 4 rectangles. This type of a Riemann sum would be called a midpoint sum, and that's the topic of our next video in the series. Thanks for watching, everybody. We'll see you in the next video.